Okay, let's begin. Thanks everyone for coming. It's so nice to see all of your happy faces here. Oh, can you hear me? Oh, people in the back? Oh, okay. All right, how about now? Better. Okay, I can do this. All right, my name is Jim McClure. I'm a professor of mathematics at Purdue, and I'm the president of the Society of Catholic Scientists chapter at Purdue. The Society of Catholic Scientists is an international organization that's been around for, I guess, about 13 years. Let's see. I'd like to briefly thank our co-sponsors. First of all, St. Tom's has been tremendously helpful in getting this organized with us, and also the Thomas Aquinas Foundation and the Purdue Religious Studies program have been helpful to us. Our speaker today is Professor Jonathan Lunine from Cornell. He's the David Duncan Professor in the Physical Sciences at Cornell University and chairman of the Department of Astronomy. Professor Lunine does research in astrophysics, planetary science, and astrobiology. He's a member of the National Academy of Sciences, and among other awards, is the recipient of the Jean-Dominique Cassini Medal of the European Geosciences Union and the Basic Sciences Award of the International Academy of Astronautics. He's the author of a textbook, Astrobiology, a Multidisciplinary Approach. And I'd like to mention that after the talk, some of us from the Society will be out in gathering space with sign-up sheets. If anybody would like to give us their contact information, if you'd like to know more about us. Professor Lunine's title is Father Lemaitre, the Catholic priest who discovered the Big Bang. Let's welcome Jonathan Lunine.
Thank you very much, Jim. And can everyone hear me okay in the back? Okay, wonderful. Well, it's a real pleasure to be here, and especially to be here in this very, very beautiful sanctuary, this beautiful church. You are all very blessed to have this parish and to have the Dominicans here with you. I spent 5 months at the Dominican House of Studies in the spring on a sabbatical, and it was 5 absolutely wonderful months that went by way too fast. When I converted to Catholicism in 2007, which was a very long road that started when I was a teenager, and I was not a teenager in 2007, you can know that. One of the things that quickly sort of came to my consciousness was this perception that somehow science and faith are two separate, competitive aspects of human existence. It was not something that I had encountered very much before I made the decision to convert, but I was very sensitive to it afterwards. And one of the things that led to was a conversation with Professor Stephen Barr in 2014, which led to the formation of the Society of Catholic Scientists, which chapter you have here at Purdue. But the other thing that it led me to was to try to find examples of scientists who also were deeply faithful in their religion, and particularly Catholicism. And Georges Lemaitre is probably the exemplar of someone who had an extraordinary depth of ability in science, was a pioneer in cosmology. I'll explain what he did. And also, more than a faithful Catholic, felt deeply that contemplating the universe was one way of appreciating our Maker, our Creator of all things. And he was very articulate about that. You'll see some of those quotes a little bit later on. So I'm going to take you in the next 45 or 50 minutes through Lemaitre's scientific contributions. I will talk a little bit about general relativity in order to give you an appreciation for that. My lecture will not allow you to get course credit in the physics department here, but it hopefully will be edifying. And then I'll talk about Lemaitre's religious views and how he saw science and faith as being harmonious. And if I have any time left afterwards, I want to talk about other things that the Roman Catholic Church does to foster science today and has done over many centuries. So let me give you a very quick biopic overview of Georges Lemaitre. So first of all, he was Belgian. His native language was French. His last name is approximately pronounced Lumet. I'm not going to put you through the torture of hearing me try to imitate that for the whole hour, so I'm going to use the more American pronunciation of Lemaitre. He was born at the end of the 19th century in Belgium. He served in World War I in the Belgian army. He then, after that, he knew when he was a teenager that he was going to become a priest. And he was ordained in 1923, right after he did a master's degree in mathematics at Louvain in Belgium. And that would be the university where he would be a professor for most of his adult life. He was then given permission by his superiors to travel to England and the United States to pursue work in general relativity. That was the subject of his master's thesis, and to pursue a PhD degree, which he obtained at MIT in 1927. And then the rest of his life he spent at the University of Louvain. So he won a number of prizes. I'll refer to the Franck Prize toward the end of the talk. That was actually the most lucrative prize at the time, except for the Nobel Prize. He was nominated by Albert Einstein, which tells you what Einstein thought of Lemaitre. He won the Eddington Medal in 1953, and he became the president of the Pontifical Academy of Sciences, which we'll talk about at the very end if I have a little bit of time. So that's his biography overall. It was really very much an academic life, a professorial life, but life as a Catholic priest and professor and scientist. So to appreciate Lemaitre's contributions, we have to go back and imagine what people thought the universe was like at the time that Albert Einstein published his general theory of relativity, which was 1916, 1917, so a little bit more than 100 years ago. At the time, the assumption by most astronomers was that the universe was static, that it was eternal, and in fact, the universe as it was known was smaller by a lot than the universe that we understand today. And in particular, things that we understand today to be galaxies, self-gravitating systems of stars that are outside of the Milky Way galaxy, were at the time thought perhaps to be clouds of gas with some small collection of stars inside our own Milky Way galaxy. Our Milky Way galaxy, we know today, is just one of hundreds of billions of galaxies scattered across the cosmos. But that was not known at the time, in the 19-teens, and it would be a few years before large telescopes were available, came online, and the size of the universe and the real identity of these galaxies was understood. So when Albert Einstein conceived of and wrote the papers on general relativity, he thought the universe was static. Now, what he was doing was conceptualizing a model for the force of gravity, which was profoundly different from anything that had been considered before, and in fact different from the other forces of nature that we're familiar with. In his model, the force of gravity is a manifestation of the curvature of space. And space itself is not the only set of coordinates in reality. There is also time. So really we live in a four-dimensional reality of space and time, where time, with a little multiplication factor called the speed of light, can be treated like another coordinate, although it behaves differently from the spatial coordinates. So Einstein, in these papers, argued that the perception that things are attracted to each other by their mass is simply a manifestation of the fact that matter curves space, it distorts space. And so he put together this big mathematical formalism, which you'll see one equation, one example of a little bit later. But he also realized he had a problem, that if matter curves space, and if the universe is static, what is it that's actually holding up the universe? The universe is filled with matter, matter attracts itself, the whole thing should collapse on itself, in fact, should have collapsed on itself a long time ago. So in his equations, Einstein had to introduce a repulsive term, what today you would perhaps call a fudge factor, but then was called the cosmological constant, that would simply be a property of the geometry of space that would repel everything and keep the universe in balance, so that you would have a static universe where matter tried to pull inward all of space, and the cosmological constant would push it out. He didn't particularly like this. It seemed rather ad hoc to him, but he didn't see any way out because he thought the universe was static. Now, a few years after Einstein's papers, a Russian mathematician named Alexander Friedman produced a whole range of solutions to Einstein's relativity equations in which the universe could be static, it could be expanding, it could be contracting. And he noticed that the expanding universe versions would obviate the need for a cosmological constant. When Einstein read these papers, he thought it was an abomination, the idea of having the universe expanding. There was no evidence for it at the time. Friedman died in 1925, and had he not died, he was a young man, he died of food poisoning. Had he not died, he probably would have played the kind of prominent role in understanding the expansion of the universe that Lemaitre ultimately ended up playing. We don't know that for sure. Friedman was in the Soviet Union, he was somewhat isolated, but the fact is he produced this mathematical abstract treatise, independent, data-free as we call it, didn't have access to the data, and then he passed away. Now, the alternative to Friedman's expanding universe models were models by a mathematician named Wilhelm de Sitter, who also was familiar with relativity, and there he is, in fact, with Einstein. He avoided this problem of matter pulling all of space together by postulating a universe with no matter in it. The universe was empty. And in that way, space would be perfectly content to avoid collapsing. Now, you might think this is a little bit artificial because, in fact, there's plenty of matter in the universe. But you could argue that the universe, relatively speaking, is dilute. And so it's not too far from reality. And one of the interesting properties of that model is that if you put two galaxies in this empty universe, they will actually tend to move apart from each other, which was a clue that the universe really had to be dynamic. So that's called the de Sitter model of space and time. Okay, so what is it that Lemaitre did? Well, when Lemaitre came on the scene, he had done his master's thesis on general relativity, describing how it worked. He then went to England and worked with Arthur Eddington, another person who began to work on general relativity. And then he came to MIT, actually came to Harvard College Observatory, where he worked on astronomical data. He worked with a famous astronomer named Harlow Shapley, and he actually did some of the work necessary to establish the distance scale of the universe. He got his PhD from MIT because Harvard at the time didn't grant PhDs in astronomy. Now, I'm emphasizing the point about the data because what makes Lemaitre different from Friedman and from de Sitter and from Einstein is that he actually tried to construct a model of the universe that was consistent with the data that were starting to be known at the time, namely that galaxies were outside the Milky Way, so the universe was large, and some of those galaxies, the most distant ones, were moving away from our own galaxy. I'll talk about that a little bit more in a minute. So Lemaitre actually developed a model for the universe, a cosmological model, that incorporated, was consistent with the data, and was a dynamical model in which the curvature of space decreased with time. Now, what does that actually mean? So to understand what that means, you have to understand what it is that general relativity does, what the field equations do. So when someone solves the equations of general relativity, they write something called a metric. And a metric is essentially a set of equations that tell you how to find distances in terms of the coordinates in space-time. So they describe the geometry of space-time. A flat space-time metric looks like this. And we kind of feel like we live in a flat space-time. Triangles, the number of the degrees of all the three vertices of the triangle add up to 180 degrees, for example. Parallel lines remain parallel over long distances. But in fact, that is something of an illusion. Space itself is and could be curved. And it's an illusion in the same way that we think that the Earth is flat, when in fact the Earth is actually not flat. It is a curved ball, and we live on a curved surface. The Earth has positive curvature. The metric of the Earth is such that if you add up the angles of a triangle that's laid out on the Earth's surface, they actually don't add up to 180 degrees. So another kind of metric would be the space-time around a black hole, where the matter in the black hole is pulling space down in this way. And then the one that Lemaitre thought up was a universe of positive curvature, kind of like the surface of the Earth, but representing the entire universe. Now, the surface of the Earth is 2 dimensions. You have to imagine this positive curvature not in 2 spatial dimensions, but 3 spatial dimensions, which is hard for us to do because we're 3-dimensional creatures. But that is the equation that Lemaitre wrote. And when he allowed for that curvature to be time-dependent, and he put that into the Einstein field equations, the whole universe became animated. It became this place in which space is expanding over time. The curvature is getting less and less in the same way that a balloon, as you inflate it, the curvature of the surface gets less and less. And what he found was 2 things. One is that at large times, his universe model was consistent with the de Sitter model because the matter in the universe became very dilute. At early times, it's like Einstein's equations, but he didn't require a cosmological constant because the curvature would get less and less with time. The universe would expand and expand, and that would obviate any possible collapse. So that was very, very innovative. And it was something that Lemaitre published in 1927. Now, there's a lot of discussion about who really thought up the expanding universe first. Was it Friedman? Was it Lemaitre? There were 2 others who worked on this about a decade later, Robinson and Walker. They are all credited with this basic geometry called the Friedman-Lemaitre-Robinson-Walker metric. But the important point about this is that it resulted in, his model naturally results in a relationship between the distances to galaxies and the velocity with which they are moving away from us. And that's what I want to get to next. So what Lemaitre set Lemaitre apart is he was the first to really confront the data, and his solution naturally implied a simple relationship between distances to galaxies and their recession. Now, I don't have time to talk about how distances to other galaxies are determined. We teach that in astronomy. It's called the cosmic distance ladder. But I do want to tell you about how recession velocities are determined. And they are determined by looking at spectra of galaxies. And this was work that began in the late 19-teens and through the mid-1920s. And so a spectrum of a luminous object is simply the distribution of light as a function of wavelength. We perceive wavelength of light in terms of color. Long wavelength is red, short wavelength is blue. But you can actually think of the distribution not in terms of color, but in terms of a sort of a line on a graph, where if you have more light coming at a certain wavelength and less light at another wavelength, that gives you a distinct spectral signature. It turns out that atoms and molecules have very distinct spectral fingerprints. They emit light or absorb light at very discrete wavelengths that can be determined in the laboratory. And it was in this way that in the 19th century, the composition of stars was determined. The elements in stars could be determined by comparing these spectral lines with what was measured in the laboratory, the lines in the star and the lines in the laboratory, using a telescope. What astronomers found as they looked at other galaxies was that the pattern of lines in these other galaxies were preserved. It was the same elements in these other galaxies as in our galaxy, in the stars of the other galaxies and the stars of our galaxy. But those lines were shifted. The whole set of lines representing the elements were shifted either to the blue or to the red. Now that shift can be interpreted as something called a Doppler shift, where if an object is moving away from you, the light will be shifted to the red. If it's moving toward you, the light can be shifted to the blue. And the same thing happens with sound waves. If you hear a car horn and the car is approaching you, and then it goes past you and goes away, the pitch initially is high, and then the pitch gets low as the car is moving away. That's the Doppler effect. So astronomers were able to map out the velocity of these different galaxies relative to our galaxy, and what they found was that most galaxies that were relatively far from us, the ones that were not part of our local group, were moving away from us. And in fact, the farther away a galaxy was, the faster it was moving away from us. That relationship is actually a linear one. It turns out from the observations that the relationship between the distance to a galaxy and its recession velocity is linear. It's the equation of a straight line. That relationship traditionally is taught to have been first published by the American astronomer Edwin Hubble in 1929, based on the data that came out from his and other observational astronomers' work with big telescopes. They found that there was this simple relationship. The speed of a galaxy away from us is just proportional to the distance of that galaxy, and the proportionality constant came to be known as Hubble's constant, and this little simple formula became known as Hubble's law. But actually, Lemaitre published this relationship 2 years before Edwin Hubble, and he published it based upon his model for the expanding universe, his solution to Einstein's field equations, and the metric that he wrote that he put into those equations. The simple linear relationship just comes out directly from that solution to Einstein's equations. And it's published for all to see in 1927 in the Annals of the Scientific Society of Brussels, and is published in French. Now, French was not the lingua franca of astronomy at the time, and this was not a very well-known journal, and there was no such thing as the internet. So astronomers got their journals by library subscription in a brown paper wrapper, probably months after the thing was mailed because it would go on a ship. And so this was actually almost completely ignored, this paper. Lemaitre's paper, had it not been ignored, would have given him credit for what's now called Hubble's law. The other important point that Lemaitre made in that paper is that this red shift that's seen in these galaxies that are moving away from us is not, strictly speaking, the Doppler shift. Doppler shift is the result of relative motion between the observer and the thing that's moving in fixed space. What Lemaitre was doing instead was having space itself expand with time. And so we can see this in this analogy of a balloon. If I represent the universe, now I'm going to take only two of the spatial dimensions of the universe. So I'm going to think of the universe as the surface of this balloon. And I have an observer here, which is me. And I launch a ray of light with a certain wavelength from a distant galaxy. If that is static, then that wavelength will be preserved moving through space. And the wavelength is given by the blue bar. But if, on the other hand, the universe has expanded in the meantime, the curvature of space is going down. We do that by blowing up the balloon. Then, in fact, by the time the light reaches the observer, the light has been stretched out. The wavelength has become longer, so that what we see at the Earth is a red shift. The wavelength of light of the distant galaxy has been stretched out by the expansion of space. So these galaxies are not moving relative to us in a fixed volume of space. They are being pulled by the expansion of the universe. They are caught in the flow of expanding space. And that is something that Lemaitre understood and, in fact, quantified. Now, Lemaitre's paper did eventually get published in English, and it got published in English because Eddington, his former advisor, having read that paper, gave a talk in which he attributed this particular solution to the Einstein equations to himself. He had forgotten that he had read Lemaitre's paper. So when Lemaitre, by that point, was a professor at Louvain, a newly minted professor, sent a letter to his former advisor saying that Eddington's suggestion of this intermediate solution was one that Lemaitre had made 2 years before. And to his credit, actually, Eddington realized that he had just forgotten that. And so he arranged for Lemaitre's paper to be translated into English and published in a journal that was very widely read at the time, the Monthly Notices of the Royal Astronomical Society. And so there it is. There's the same paper in English, published now in 1931, 4 years after it was published in French, and 2 years after Hubble published what became known as the Hubble law. Now, you would think that Lemaitre would then get credit for Hubble's law. Unfortunately, he did not, because the key portion of the French paper that establishes what we call Hubble's law was actually missing from the English translation. And for many decades, this was somewhat mysterious and the subject of conspiratorial speculation. Maybe Hubble arranged to have it omitted, when in fact, it turns out, and this was determined by an astronomer, Mario Livio, at Space Telescope, he found out why this happened by looking through the files of the Royal Astronomical Society. It turned out that Lemaitre had done the translation himself, and he had actually deleted the paragraph. And he deleted the relevant paragraph because he in this paper was comparing the linear relationship, or tying the linear relationship, to the data available in 1927, which was much more sparse than the data available in 1929 when Hubble published his paper. And so Lemaitre, in his cover letter to the editor of this journal, said that he omitted that because it was no longer of current interest. Now, there's some debate in the last year or two about whether the editor of that journal had first written to Lemaitre saying maybe you should leave that part out, or whether Lemaitre did it himself. But the fact is that he lost the chance to be credited with predicting the most famous relationship in modern astrophysics, one that came directly from Lemaitre's model of the geometry of space-time, but became associated with Edwin Hubble. And the irony in all this is that Hubble himself never accepted the idea that the universe was expanding. He was not a mathematician. He was not a physicist per se. He was a great observer. He was also a great fundraiser. He basically got the observatory on Mount Wilson built. He would bring famous luminaries like Albert Einstein up to look through the telescope and make sure that he had his picture taken with them. There's Hubble in the background. But he didn't believe the universe was expanding. And in fact, in this interview with him, or this report of an interview with him from the Los Angeles Times in 1941, it says straight out that Edwin Hubble says the universe is just perfectly tranquil and static. So Lemaitre would have ended up being relatively obscure, except that he got into a debate with his former advisor Eddington about what it meant for the universe to be expanding. What if you roll the tape back in time? What if you imagine the universe going back in time, getting smaller and smaller and smaller? What's the end state of that? Eddington said that he couldn't imagine that the universe really had a beginning, that somehow something must have happened early on to sort of stop this or change this flow of time. Lemaitre disagreed with that, and he wrote a letter to Nature in response to Eddington, which is in fact the letter that establishes Lemaitre's priority in inventing what we now call the Big Bang model of the universe. Because what this article actually says, it's not on there. What this article says, and we'll see a few words from it later, is that the universe actually had a beginning in time. And at that beginning, everything was so compressed, just run the tape backwards of his expanding universe. The universe was so compressed that all matter was a single quantum or a single atom. And he actually began to think about how the quantum mechanics of the time, the uncertainty principle, and so forth would cause matter to begin to split apart as the universe expanded. That's an interesting side issue. He was one of the first to try to combine quantum mechanics and general relativity. But what was important about this letter is that it is the document in which Lemaitre first says the universe had a beginning. He didn't call it the Big Bang. He called it the primeval atom model. It would later be called the Big Bang by one of his opponents, Fred Hoyle. So it's this little short letter to Nature that establishes for Stephen Hawking and for all astronomers today pretty much what everyone accepts, that Georges Lemaitre was really the first to investigate a finite age, a beginning, a definite beginning to the universe, what we now call the Big Bang. So that is what he is most famous for, even though this really comes out of his 1927 paper, which was a far more profound piece of work than just this letter in Nature. All right, so Lemaitre did a lot of other things, and I'll briefly talk about them at the end. But World War II came and went. Very little work was done. And after World War II, when astronomers began thinking about this again, there was considerable opposition to the idea that the universe had a beginning. And in fact, some astronomers argued that this was a religiously motivated model. In particular, the British astrophysicist Fred Hoyle, who began to do his work in the 1940s and was a great public speaker on science, a kind of a Carl Sagan of the 1940s, argued that the primeval atom model was actually motivated by religious bias because it sounds like the book of Genesis. In the beginning, there was a beginning. Lemaitre, on the other hand, and Hoyle, in fact, being a colorful character, referred to Lemaitre's model as the Big Bang in a sort of a sarcastic way, and to Lemaitre as the Big Bang Man. So that's how the model came to be known as the Big Bang. Now, Lemaitre himself argued there was no religion in this whatsoever. It came from his model, of general relativity. So Fred Hoyle, together with two others, Tommy Gold and Herman Bondi, cooked up a competing model, which they called the steady-state model of the universe, in which there is no beginning to the universe. The universe really is infinite in time. And yet they realized that the universe had to be expanding, otherwise it would violate general relativity. You'd need a cosmological constant, a fudge factor, and so on. So how do you have the universe expanding over an infinite amount of time and still have a finite density of matter in it? We wouldn't see any other galaxies. So what they postulated was that there was some process by which individual hydrogen atoms would pop into existence, and they would then compensate for the expansion of the universe. So the steady-state model required that matter be created, admittedly very slowly, and only a few hydrogen atoms per billion years per cubic kilometer. But there was no mechanism for doing this. So that was the competing model. Now, Lemaitre, as I said, argued there was no religious motivation for his model, but Pope Pius XII, who was the Pope at the time, helped the other side by giving a very famous speech to the Pontifical Academy of Sciences in 1951 called the Fiat Lux speech, Let There Be Light, in which the Holy Father, who was very interested in science and wrote brilliantly, argued that the Big Bang itself, this bursting forth from nothing, a sea of light and radiation, elements splitting and churning, forming galaxies, this is Lemaitre's model, that this confirms the contingency of the universe, hence creation took place, hence there's a creator, and therefore God exists. And so that speech played into the hands of people like Hoyle and others who said, aha, this is a religiously motivated model. Lemaitre himself was actually quite horrified. And when he heard this speech as a member of the Academy, and when he learned that the Holy Father was going to give the same speech to a much larger group of astronomers the next year in Rome, the International Astronomical Union, actually intervened with the Pope's advisors and managed to talk the Holy Father into omitting this part of the speech, which he did the next year. That part does not appear. Nonetheless, the damage was done, and Lemaitre always felt a little bit besieged by his non-believing opponents who argued that he had cooked this model up effectively from the Bible. But it turned out that Lemaitre was right. And what tipped the scales in favor of the Big Bang model was that it predicted that as the universe expanded and cooled, there must come a point where, prior to that point in time, the universe is hot, all the atoms are ionized, the electrons are separate from the atomic nuclei, light is trapped within this milieu of charged material. As the universe expands and cools, there comes a point where the atoms can combine and become neutral. The electrons can join into the atomic nuclei, become bound to those nuclei to make the neutral atoms like what we have in this room and in our bodies. And then light is free to move through space. In Genesis, the light is separated from the darkness. That moment is visible to us. Because it happened everywhere in this expanding universe, it's all through and around us. But because the universe has expanded from that very early time, which was about 400,000 years after the Big Bang, to today, that signature of the light being freed from the material universe is now redshifted into the radio part of the spectrum, the microwave part of the spectrum. And so the prediction was made not by Lemaitre, but by others, that there should be this uniform static in the cosmos. And sure enough, in 1966, Penzias and Wilson, with a new radio telescope, found that static, what we call today the microwave, the cosmic microwave background radiation. And it has absolutely no equivalent in the steady state model. In fact, when Hoyle learned of this, he admitted that the steady state model had to be disposed of. Lemaitre also found out about this. He found out about this on his deathbed. He was dying of leukemia. And within just a few days of his death, he knew that his primeval atom model was actually correct. And it is still the model with some modifications that cosmologists use today. I want to say a little bit more about Lemaitre's other contributions. I'm only going to give you one example, and then I want to talk for about 15 minutes about his, what he had to say about faith and science. So here it is. Here are the Einstein field equations written in a very compact form in which the different dimensions are combined in these subscripts, spatial and temporal dimensions. This kind of mathematical construct is called a tensor. And what this equation essentially says, G here is the bending of space, T is the matter energy content of the universe. And what this equation says in words is that matter tells space how to bend, and the bending of space tells matter how to move. And here is this fudge factor, this lambda with a little g, which is the cosmological constant. In a later paper after the primeval atom model, Lemaitre proposed that one could think of the cosmological constant not as a geometric factor, because everything on the left side of this equation is geometry, and everything on the right side is the physics, the matter and the energy. Why not move the cosmological constant over to the other side of the equation and call it some sort of intrinsic energy of space that tends to push things apart? Lemaitre was the first to do this, and he did this in a paper in 1933, and it's recognized today, this is a quote from Robert Kirshner, that Lemaitre's interpretation of the cosmological constant is shockingly modern. It's more or less what people talk about when they talk about dark energy today. But this was done 50 years before any evidence for dark energy would really appear in the astronomical data. Lemaitre didn't do anything else in general relativity. He began to work on other things. Cosmology moved from solutions to general relativity to things that had more to do with nuclear physics and how atoms and subatomic particles behaved in the early universe. He began to work actually on numerical methods and was a pioneer in digital computing in Belgium. But here he is in 1957 with a number of astronomical luminaries at a Vatican study week on stellar populations. So there's Lemaitre, there's Fred Hoyle, there are a number of other famous astronomers here. This is Ed Salpeter, who was a young man at the time, and he was just starting at Cornell, which is where I work. And I show this picture because one of his PhD students, much later than this picture in the 1970s, was my thesis advisor. So this is my grand thesis advisor here with Georges Lemaitre and Fred Hoyle. That's the closest I ever got to Georges Lemaitre. All right, so let's talk about Lemaitre on questions of time, creation, and God. Lemaitre thought a lot about the religious implications of his work, but he would hide these things in his writings in a sort of a very clever way. So first and foremost, this famous short letter in Nature, here is from the first paragraph of this paper. a statement that's underlined about the idea that time began when the expansion of the universe began. Time began with the expansion of this single quantum, this primeval atom. And he wrote, if the world has begun with a single quantum, the notions of space and time would altogether fail to have any meaning at the beginning. They would only begin to have a sensible meaning when the original quantum had been divided into a sufficient number of other quanta. So start with one single quantum of matter and divide it up. The beginning of the world happened a little before the beginning of space and time. The funny thing about this, the way he wrote this, is it's almost exactly the way that St. Augustine expressed the beginning of time in the City of God in 426 AD, where he wrote, if eternity and time are rightly distinguished by this, that time does not exist without some movement and transition, while in eternity there is no change. Who does not see that there could have been no time had not some creature been made by which some motion could give birth to change? If you take the word creature out and put in quantum, it's the same basic idea. And then St. Augustine goes on to say, then assuredly the world was made not in time, but simultaneously with time. It's the same structure and essentially the same wording. Whether Lemaitre deliberately did this as a way of kind of secretly referring back to St. Augustine isn't clear. He doesn't reference the City of God in the bibliography. Lemaitre also talks about the hidden God a lot in his work, and he nearly published a paragraph about this in that famous Nature letter. This is from a manuscript version of that article, which is in the archives in Louvain, and there's an extra paragraph here. The actual article in Nature ends with the word step by step, but here in this manuscript there's another sentence which reads, I think that everyone who believes in a supreme being supporting every being and every acting, his English was not perfect, he meant action, believes also that God is essentially hidden and may be glad to see how present physics provides a veil hiding the creation. God is hidden in the laws of physics. God is, now I'm extrapolating, but he did have a somewhat Thomistic education. God is the uncaused first cause of everything. All of the physics, all of the chemistry that we do, those are the instrumental causes through which the uncaused first cause creates and expresses the universe. And that's hinted in here in this, which never made it into the letter to Nature. Pencil mark drawn through it, clear that he decided, no, he'd better not put that in his letter to the journal Nature. But it's there, the hidden God. Lemaitre was, I think he was a good Thomist. He thought a lot about the question of whether the Big Bang was a beginning or a creation. He distinguished between those two things. A lot of astronomers, when they criticize the idea of God being behind all of reality, confuse the beginning with creation. They think of God as some sort of a magician who lights a bit of flash paper and gets the universe going, rather than, as St. Thomas said, God actually holds all of reality as real at every moment in time, and that all of creation has this radical relationship to God, and it's for that reason that we actually exist. Lemaitre said, we can speak of the Big Bang as a beginning. I do not say a creation. Any preexistence in the universe has a metaphysical character, and the question of whether it was a beginning or a creation, something started from nothing, is a philosophical question which science cannot answer. And that is very important. The limitations of science in what we can do in studying the material universe, it's very important to recognize those limitations extend to the question of why is there something rather than nothing. It is not a scientific question. Lemaitre also addressed the famous statement that Einstein made that the eternal mystery of the world is its comprehensibility. Lemaitre's response to that in an address in the same year is to say that while both the scientist believer and the scientist non-believer attempt at decoding the the hints of nature, the palimpsests of nature, the believer has an advantage of knowing that the riddle possesses a solution because its degree of difficulty is measurable with the present and future capacities of humanity. And he goes on elsewhere to explain what that means, that God wants humanity, humankind, to appreciate and understand the majesty of his creation, and so has given us a mind that is able to do that, albeit in a limited way, but still in a way that allows us to appreciate it on the scale that Lemaitre is alluding to here. I'm not going to read this one, but Lemaitre was very firm that the Bible is not a textbook of science, that there is no controversy between religion and science, that the Bible tells us the story of the salvation history of humankind. It's not a textbook of natural history. And he goes on to explain that neither St. Paul or Moses would have had any understanding of the theory of relativity, because it's not necessary for salvation or for the revelation that they provide in the Bible. And so he was very firm about this through his whole life. He said that there are two paths, two ways of arriving at the truth. He's followed them both. One is his faith and one is his science. And he says, nothing I've ever learned in my studies of either religion or science has caused me to change that opinion. I have no conflict to reconcile. Science has not shaken my faith in religion, and religion has never caused me to question the conclusions I reached by scientific methods. 1933. So I'm going to end. I'm not going to talk about the other activities of the church in science because I'm out of time. I want to end with Lemaitre's legacy. He was a remarkable mathematician and cosmologist. The list of things that he did in the period from 1927 to 1934 is really extraordinary. And I'm not going to go through all of these, but the idea of the expansion of the universe starting from a Big Bang, the role of the cosmological constant as a vacuum energy, a number of other things. This is very interesting. This was pointed out by a colleague of mine at Cornell. It was actually Lemaitre that solved a confounding problem in the mathematics of black holes from the 1930s. The person who first described a black hole mathematically long before they were discovered was a guy named Schwarzschild. And he had a mathematical picture of a black hole that not only had a singularity at the center, a violation of physical laws there, but he had one at the surface as well, which was kind of problematic. Lemaitre actually fixed this with a very clever coordinate transformation that's in his dissertation in 1925. So the picture of black holes that we have today is really not just from Schwarzschild, but it's Schwarzschild and Lemaitre. Again, Lemaitre doesn't get any credit for it. So I'm only going to read one of these. The demonstration that our physical universe expanded from a very different state grew out of advances that to a striking degree were the work of a single person, Georges Lemaitre. That is P.J. Peebles, who won the Nobel Prize for Cosmology in 2019. Finally now, after a period in which Lemaitre's work was really neglected, he's coming to be recognized as having played a titanic role in our understanding of the expansion of the universe. And in 2018, a resolution was introduced at the International Astronomical Union meeting to rename Hubble's law as the Hubble-Lemaitre law. It passed by 70%. Those who opposed it said, well, not everyone who's an IAU member was there at the meeting. So the president of the IAU at the time, who is shown here with me last week when I was in Rome, said, okay, we'll do the vote online, and it was still 70%. 70% of astronomers said, yes, Lemaitre should be given credit with Edwin Hubble for that law. I think it should be the Lemaitre-Hubble law, not the Hubble-Lemaitre law. That's another story. Okay. So, remarkable scientist, very faithful Catholic, articulate on both areas. And when he was accepting the Franck Prize in 1934 as a young man, in his acceptance speech, he put the two together, science and faith. He said, science is beautiful. It deserves to be loved for itself as it is a reflection of God's creative thought. Thank you very much.
Well, I think we have time for a few questions if anybody would like to ask anything.
Don't be shy. Yes.
Okay. John is never shy.
Okay.
So when I read the quote that you had of Pope Pius,
The 12th, yep.
I was a little confused. I don't understand why Lemaitre was horrified by that. To me, when I read it, it just seems like the Pope is saying science has sort of rediscovered stuff that we were thinking before. It doesn't,
Right.
but it doesn't seem to me to be offensive. So why was he horrified by this?
Yes. So the easiest way to think about it is to put your atheist hat on for a moment, okay? And so the Pope said, the Pope described this model with this brilliant language. He was an excellent writer. He was really interested in science. He talks about the expansion of the universe. And he says, and then, because of that, the universe must be contingent, and therefore then there must be a creator, and therefore God exists. His atheist opponent said, aha, you actually have to take that reasoning and run it backwards, because Monsignor Lemaitre believes that God exists. He cooked up this model so that you would have some demonstration in that way that God exists. If you think about it the other way around, if you wanted to have a model in which the expanding universe demonstrates the need for a creator, you would have a finite starting point in time. And that's really what Hoyle and others were accusing him of, was saying that the expansion of the universe required that there be this finite start, because by doing that you had to have a creator. And so that's really what their objection was. Now, how do you get an expanding universe without having a finite initial point in time anyway? Of course, it turned out that his model was demonstrated a decade and a half later by the radio astronomy results. But you could fiddle around with the math and have the expansion sort of be logarithmic back to the past, so that it asymptotically sort of, becomes a kind of incremental expansion and takes an infinite amount of time to go to zero or something like that. That's what they were trying to argue for.
Yeah, I would say the competing model, the steady state model, that was much more obviously cooked up to fit a preconceived notion of how the universe was.
Well,
so
Hoyle,
it was really the other way, the other side that was doing that. But.
Hoyle admitted that, actually. And in fact, the story is that it was cooked up when they were watching a movie one evening that had a sort of an endless cycle, a plot line in it. But he, to his credit, Hoyle gave up that model, and actually so did the other two as well. Yeah.
Other questions? Okay.
There's one behind you. Go ahead. And then there's one over there in the red shirt. And yeah. Okay.
So this isn't meant to discredit any of the father's his works, but I believe once I read the James Webb telescope, I think that's what it was called, found evidence that may have disproved the Big Bang Theory, but apparently the Big Bang Theory is still the leading theory in the scientific community. What evidence is still there is there any reason why it's still the leading theory?
Sure. Okay. So thank you for that question. So you mentioned the James Webb Space Telescope. And actually, that meeting I was at in Rome with the person who introduced that resolution, that was actually a meeting exploring some of the results of the James Webb Space Telescope. We actually it was held at the Pontifical Academy of Sciences. So the Webb telescope has allowed astronomers to look even further into the universe than the Hubble Space Telescope did. And the further you look, because of the finite speed of light, the farther back in time you're looking. And in the meantime, the universe is expanding and stretching outwards. So the galaxies that we're seeing with Webb are going back 13.4, 13.5 billion years in the past, within the first few 100 million years of the beginning of the universe. But their distance is stretched out by the expansion of the universe to about 40 billion light years. One of the things that Webb has shown that's a little bit surprising is that those galaxies, which should be very young, because we're seeing them near the beginning of the universe, are already pretty well developed. They're very luminous, they seem to have structure. That was not predicted by models of galaxy evolution. It's a little bit like if you walked into a kindergarten knowing that all the kindergartners were 5 years old, but they all looked like teenagers or college students. You'd think, how did they grow up that fast? So that by itself doesn't directly challenge the Big Bang model. What it says is that somehow things happened faster in the early universe than they happen today. The Big Bang model, what's called the standard model of cosmology, has been remarkably resilient to various discoveries over time. There's some modifications to it, but it always still comes back to the idea that somehow the universe 13.8 billion years ago was incredibly small, incredibly dense, incredibly hot, very different from today. That is still part of modern cosmology. So thank you for the question. I know there was someone who had hand up who has a red shirt right there. Okay.
I wanted to ask, I think in the current year, when I hear the Big Bang Theory mentioned outside of like scientific context, it is as a counter theory to the universe being created by God. Why is that? Why is it that in the current year it's more of an atheistic thought of a Big Bang rather than a theological one, as it was perceived in the around the time that the theory came out? Thank you for your speech, by the way.
Sure. Thank you for the question. So you're absolutely right that very prominent cosmologists like Stephen Hawking in particular have tried to construct a model of how the universe began, consistent with the Big Bang, but with a fixed set of what are called boundary conditions that automatically cause the universe to start expanding. And that Hawking argued, because he could do that, obviated the need for God. That, you know, if you could describe with equations how the universe begins expanding, and it begins expanding in those sorts of models from a sort of a quantum vacuum that has fluctuations in it, then there's no need for God to start the universe. So there are three responses to that very quickly. The first is that this is confusing, again, the beginning with creation, as Lemaitre said. You know, Lemaitre's point of view, we will never know if it was really Thomistic, but a Thomist would say that God didn't show up at the beginning, start the universe, and then leave. God is being itself. God's essence is being with a capital B and holds all of reality in being all the time. And so actually, for St. Thomas, the universe could have been infinite all the way back in time, and that to him didn't say anything about whether God existed or not. He said God would exist whether the universe was eternal or not. That was written in the 1200s. So that's point number one, confusing a beginning with a creation. Point number two is that all of these models in which you have something that sets the universe off, like a quantum vacuum with fluctuations, you're still starting with a thing. You're starting with quantum fluctuations in some substrate of reality that we don't experience today. what created that substrate of reality? What created that space that has these fluctuations in it? That space is not nothing with a capital N. It's something. It's just different from what we have. So you still have to explain why there is something rather than nothing. And the third answer to that is Hawking gave up. He changed his mind on that. And he and Thomas Hertog, his last student, have now argued that, that the idea of trying to explain the beginning with physical laws is not possible. And instead, what his student is offering is something called the no boundary model, which I don't have time to explain, but I'm happy to talk about out there, where time itself sort of fades away as you get back to what we would call the beginning. So Hawking, before he died, actually, there were different epochs of Hawking. The sort of super atheist Hawking went away in the last year or two of his life. And he argued that you really couldn't just write a set of equations that would tell you how the Big Bang happened.
Okay, one more question.
Yep, over there.
Okay.
Thank you. My question may be similar to hers over there. I've heard people say that scientists today are perhaps less confident in the Big Bang theory, and they'll say things like, it may not have actually been an initial singularity, or that it might have been like that it's cyclical, a universe that expands and contracts kind of perpetually. So I just didn't know if you had any additional thoughts about that.
Yeah, you're absolutely right. And actually, Lemaitre himself had a paper on what he called phoenix universes, which is that one universe would rise out of the ashes of a previous one. The modern version of that is something that Roger Penrose, who's a famous British mathematician who was a contemporary of Hawking, calls the conformal cyclical cosmology. And in that, the next universe arises out of the evolution of the previous universe, that you have these sorts of cycles. So that's entirely possible, and Lemaitre did think about that too. What's not likely is the idea that the universe expands like a balloon and then slows down and contracts again. What we do know from observations of the relationship between the distance and the velocity of galaxies is that our universe is going to expand forever. It's not going to slow down. It's not going to collapse. Another universe is not going to pop out of that. If you want to have a cyclical universe, you have to perform a kind of a mathematical trick, a mathematical ledger domain, which is what Penrose did, where as this universe gets to a large scale, you suddenly do a scale change, you get a small universe out of it. It's very entertaining and very tricky math. Regardless of that, the universe that we can observe has consistency with the idea that it was very small, very hot, very compact at some finite time in the past. Otherwise, we would never see the cosmic microwave background radiation. So that's the best evidence that whether it's a single Big Bang or multiple episodes, it happened.
Okay, well, thank you all for coming. And yes, let's thank the speaker again. And I'll mention again that some of us will be in the gathering space over here with sign-up sheets if anybody would like to give us contact information and would like to know more about our society. Thank you.